everyone, I am here to record a lecture on state space analysis, variable model unit 2, control system, and the course code is KEC 602. I am Pragya Srivastava, assistant professor, AKGEC, Ghaziabad. So in the previous lecture of this unit, we have studied the state space variable model and we have studied the state space equation. Presently, we are going to study further on the same equation. We are also going to discuss the examples and state diagram. So we have to see what is a state diagram. The significance of the state diagram is that it forms a close relationship among the state equations and the computer simulation and transfer functions. So what happens presently is a state diagram is constructed following all the rules of signal flow graph and the transfer and the Laplace transform state equations. Further, in this state diagram can be constructed directly from the system's differential equation. Like previously, we have studied a numerical. From that numerical, we have studied that from the differential equation itself, we can reframe the transfer function, we can reframe the block diagram and state diagram. This allows the determination of the state variables and the state equations. The state diagram can be constructed from the system's transfer function, and this is also called decomposition of the transfer function. The state diagram can also be used to program the system on an analog computer, and we also see that state transition equation in the Laplace transform domain can be obtained from the state diagram by using signal flow graph formula. So we see that we have number of possibilities available here to study the state transition equation and how the signal flow graph, that is SFG, and the SFG gain formula helps us to retrieve and find out the transfer function. The state equation and the output equation can be determined from the state diagram itself. So moving on to the slides, we have from differential equations to state diagram. So when a linear system is described by a high order differential equation, the state diagram can be constructed from these equations. Now let us consider that we have nth order differential equation. So it is dny by dtn. So nth order differential equation will have n number of state variables we have studied previously. Let us consider a case where we have second order differential equation. In that case, we will have two, like second order differential equation, the order of the equation is 2. So we will be having two state variables, x1 and x2, and differential state vectors will be x1 dot and x2 dot. Now here we have this differential equation. We are rearranging the differential equation and we are getting it like dny by dtn is equal to, now we are just transferring all the elements on the RHS, and when we are transferring all the elements in the RHS, we will have this plus sign is minus everywhere. Now we take the Laplace, taking the Laplace transform on both the sides. Now when we are taking the Laplace transform, it becomes Sn of ys, rs, an s raised to the power n minus 1 ys. Now we are trying to make the signal flow graph. What we are actually doing is, when I am clear that we have nth order differential equation, it means I would require n number of integrators. N number of integrators means, if I talk about block diagram, I'll have n number of integrators. Okay, these will be n number of integrators. If I talk about signal flow graph, I'll be having, here it is a node, here it is a node, here it is again a node, and then I'll be having n number of integrators. So this is one and the same thing. One is the block diagram, another is the signal flow graph. So here I have S, it is very clear. So if here I have S raised to the power n here I'll have s raised to the power n minus 1. Here I'll be having s raised to the power n minus 2, because every time I'm introducing s raised to the power minus 1, I will yield s raised to the power n plus minus 1. S raised to the power n minus 1 again, I'll be having s raised to the power n minus 2. S raised to the power n minus 1 again, I'll be having s raised to the power n minus 3. So this is what we are having, s raised to the power n, s raised to the power n minus 1. Nothing to say, we have a element s raised to the power minus 1 in between them. So everywhere in between the dots, I have s raised to the power minus 1. Everywhere I have s raised to the power minus 1. So I'll just clear and I'll try to explain with the new starter. So this is the input. Input के साथ I have the multiplicative term as 1. So this is 1 is being multiplied here. So 1 being multiplied. So it means this is 1. Now I have to realize, I have to get the output at this node. So this output is s raised to the power n y of s. So this is adding all these terms. So first term is 1 into rs plus algebraic sum. So I'm putting it plus. Algebraic sum means I have to add, I have to sum with the negation. Like if it is having minus of an, I will put a gain of minus of an here. So it is minus an s raised to the power n minus 1. So s raised to the power minus n minus 1 is here. I have to just multiply it by minus of an. Then the second term, s raised to the power, let's say here I have a second term. I'll use a different ink. Let us consider I have a second term here, which is minus a n minus 1 s raised to the power n minus 2 ys. Another term is minus a raised to the power minus a of n minus 2 s raised to the power n minus 3 y of s. So this term coming with negative sign will be here. Okay. So when we add all this, this is nothing but a summation. If I talk about block diagram, this is nothing but a summation. So if I add all the terms, I will get s raised to the power n here as an output. I think I have made this point clear. Next is state diagram representation of differential equation. What I have to do, I have to make connections. Like in between, we cannot leave the branches open. So here it is a integrator. Here also we have an integrator. Here also we have n integrators. So this is the required diagram here. This is, if I take, this is the inputs, all the inputs, and this is the output, which is s n y of s. S n y of s. Now, considering another example of differential equation, here we see we have second order differential equation. We are writing it in terms of differential term d2y by dt square, and all the terms will come in the RHS. And then from here we'll convert it into S domain and we'll write it as s raised to the power 2 y of s minus 3 s ys minus 2 ys plus r of s. So r of s is just multiplied with the term 1. Why? Because here we have 1. So this is multiplied with 1. And then the first differential term sys. So here we will be having, here it is s ys, here it is ys. So sys is multiplied with minus 3, and then ys, here ys is multiplied with minus 2, and then we are adding everything, and at this node the value is s square ys. Now, this is how we have studied to realize differential equation to state diagram. We have tried to form a signal flow graph out of differential equation. Now, decomposition of transfer function. The direct method which we are going to study is here. The process of obtaining state diagram from the transfer function is called the transfer function decomposition. The objective is to construct a state diagram from the transfer function. The following steps are outlined. So, express the transfer function in negative powers of s. So, this is the first step which we have to do. Express the transfer function in negative powers of s. This is done by multiplying the numerator and the denominator of the transfer function by s raised to the power minus n. So, nothing to think that by which power I have to multiply, just multiply with the highest power, highest number, like the highest power of s. So, if it is nth order differential equation, we have to multiply it s raised to the power minus n. So, multiplying the numerator and denominator of the transfer function by a dummy variable xs. So, by implementing the last two steps, the equations is like that. So, what we are doing, this is the second step. So, first step, this was the first step. This was the first step. First step is being implemented here. We have multiplied the complete term by s raised to the power n. So, when we are multiplying the power, when we are multiplying the complete equation by s raised to the power n, so the initially also it was having s. Let's say this was having s inverse, and I multiply it by s raised to the power n. So, it will end up giving me s raised to the power n minus 1. So, this is what I have, s raised to the power n minus 1. Now, the second step, which is this one, is multiplying and dividing by dummy variable x's here and here, implemented here. This is the second step, multiplying and dividing by xs, that is a dummy variable. The numerators and the denominators on both the sides of the equations are equated to each other respectively, and the results are. So, we'll be having two equations. So, first ys into this and then us into this. So, ys, no, let me make a correction here. What we are doing, we are equating the corresponding elements, like we are equating ys with this one and we are equating us with this one, not the cross multiplication. We are just multiplying the corresponding ones. So, ys multiplied with this is in this equation, us is getting multiplied with this, giving this equation. Now, arrange above equations in such a way that the equations has inputs on the left hand side and the remaining terms on the right hand side. So, inputs on the left hand side. Now, what we are doing here is, let's say we are studying this equation. In this equation, we have input as x's and the remaining all the terms should come on the right hand side. So, this x's is coming here and we are putting all the terms on the other side. So, what we are doing here is, for equation 1 satisfied, equation 2 doesn't satisfy, and then equation 2 can be rearranged as. Now, equation 2 is this one. Equation 2, when xs is multiplied with this term, we have us plus a single term x of s, and then x of s will be there in all the terms. Now, what we are doing, we are extracting xs in all the remaining terms by taking common. So, here it is the common term multiplied with the xs, and then xs remains on the left hand side, yes, and the remaining terms comes this side. Now, we can see and make this signal flow graph just by making visual understanding. So, what we are doing, actually we have to see that from this equation, we have all the components of matrix B. So, matrix B is feed forward matrix, and feed forward matrix comes up as a parallel branches. So, we see that these are coming as the parallel branches, and this is nothing but matrix C. Yes, they are coming as a parallel branches. We can see this one, this one, this one, and the components which are available in the second equation, sorry, the third equation here, will be coming as the feedback branches. A of n minus 1, A of n minus 2, A of 1 and A naught. So here we have A of n minus 1, A of n minus 2, minus A naught. So these are coming for the feedback branches, and they end up giving us the system matrix or matrix A. So we can see, we can visualize, and we can understand the equations. I should have these two equations on this page as well, so that I do not need to change the slides every time. So let us try to understand the output of y. If I try to see what is y here, so y will be nothing but bn plus x1 dot b1 plus xn minus 1 into bn minus 2 xn into bn minus 1. So let's see, is it exactly coming? So ys is nothing but bn minus 1 into s1. So bn minus 1 into, this is the first term, s raised to the power minus 1. bn minus 1, s raised to the power minus 2. So s raised to the power minus 2 is here. Minus 1 is s raised to the power minus 2. S raised to the power minus 2 into bn minus 2. Now s raised to the power minus 3 into bn minus 3. And s raised to the power minus n into bn. So s raised to the power minus n into bn. Here we have got the output at this node. Coming on to the second equation. Here we have input multiplied with 1 minus all the terms which are coming in as a multiplicative term with s raised to the power minus 1. Here we have xn, s raised to the power minus 1 is the value, like we have only one differential vector till here. So one differential vector means I have to consider this term. Second differential term, it means I have to consider this term. Now first differential term, I am considering just first term, minus a n minus 1. Second differential term means minus of a n minus 2. And then adding all the feedback branches, we have the second equation, which is this one. So in this way, we have studied how to decompose. And this is the required signal flow graph. According to that signal flow graph, we also have these equations A, B, C and D. So once we have all these equations A, B, C and D, we can very well configure the transfer function. Here I have also previously in my previous lecture, I have seen that how matrix can be reframed from all the matrices. How the transfer function can be reframed from all the matrix A, B, C and D. In this diagram we see that we have x1, like this is the state equation, and then this is the output state equation, and we are just trying to take the Laplace of the first equation. So when we take the Laplace, x dot can be represented as s into xs plus ax plus bu. Now what we are doing, we are trying to put this term on the LHS. So b of us will be sxs minus ax, and then we are trying to have xs as common. So xs ko we have taken this common, so it will be si minus a. So when I rewrite xs in the LHS and try to put all the terms here, it becomes si minus a inverse b of us. Now from the equation 2, we are taking the Laplace, and in the Laplace itself, we will replace this xs from this equation. Now we have replaced this, and then after replacing this, we can see that this us comes up as a common term. So I extract it outside so that d comes a part of the equation, and then we have output y equals to this complete term into input u. I can divide this input and have a relation like output upon input, which is nothing but the transfer function. Output upon input, and this is the resultant transfer function. So in this, we can see that using this formula, we can get all the transfer function from the previously available matrix. So this was all about Unit 2, and we will be studying more about control systems in my next lecture. Thank you.